Hi everyone, I'm Kshitij and my topic is securing cryptographic keys using biometrics. So the motivation behind using biometrics as a crypto primitive is that biometric crypto systems are going to allow for enhanced security and they also reduce the risk of unauthorized access since the biometrics of a particular user really belong to the user and are difficult to impersonate or fake. And also they are really convenient. We can use biometrics to like almost in daily life. And also we can see here a few examples. We can see that the Apple Face ID, the many of us who have iPhones would definitely know about this. So Apple's Face ID uses the face biometric, the features in the face to unlock the phone which contains most of our private information. And also there is the Microsoft Windows Hello, which basically uses the again the face biometrics or the fingerprint to help or like secure the device that the person is using. So the use of biometrics is really important because it ensures that only the authorized persons can use it, and also biometric features are really unique to each individual. So they are a very good way to basically secure the private information that we are there, and they are also we can see used extensively throughout the daily life. So, what is the need for biometric schemes for securing the keys? So, we know that almost all of the data security that exists on the internet today or anywhere really uses cryptography, and cryptography makes use of keys, cryptographic keys that are used in symmetric ciphers such as AES, which is the modern encryption standard, or even in public crypto systems like RSA, where there is a public key and a private key pair that is used for secure exchange of messages. So that is why cryptographic keys uh, are really important, and we should really need to secure them. But the problem is that cryptographic keys are long and they are hard to remember. Uh, we as a user can remember our password easily because we can set it to something that we can easily remember, like a date of birth or something. But the cryptographic keys, to ensure the security and to make sure no adversary can effectively get the original message from the encrypted message, they have to be long and they need to be completely random, right? If they need to be not correlated with anything that can be easily found out by using something like a social engineering attack or any personal information. So cryptographic keys are long and they're hard to remember. So as a person, it is really difficult to remember, or even storing the cryptographic keys is not secure because if the cryptographic keys are exposed, all the ciphertext that was generated using that cryptographic key are basically exposed. So we need to secure these keys, but securing the keys, one approach we can take is maybe we can encrypt the key, but then to encrypt the key, we need another key, and so it becomes like a recursive problem. So this problem can be effectively solved using biometrics. The key can be bound with the user biometrics, or the keys can be generated using the user biometrics. These are two different approaches to securing the keys, and we'll take a look at both of them. But the main idea here is that the user biometrics that are readily available can be used for securing the keys. And in that case, we don't need another key to secure the key. The biometrics themselves act as a key. Uh, and we can see that for this purpose, we can use crypto primitives like fuzzy extractors, maybe like a fuzzy vault, and mathematical primitives like one-way functions, which make it impossible to go from the result of uh, the combination of biometrics plus cryptography back to the cryptographic key. So let's also take a look at key binding versus key generation. My research work is focused on both of these. Uh, so basically, the key generation involves creation of a cryptographic key from the user biometrics. So we are going to take the user biometrics and then we are going to generate the key using that. And the key size and randomness is definitely going to depend on the size and nature of the user biometrics. So, for example, if you take the minutia points of fingerprints that are present with the user, the number of minutia points that are present in the fingerprint image that is captured is going to decide how many cryptographic, what is the length of the cryptographic key that is going to be generated. So, for example, if you want an AES 256 bit key, we need a proper method that is going to generate all of these keys. That are at least 256 bits in size, so we can encrypt and decrypt plain text using the AES. Key binding, on the other hand, will bind a randomly generated crypto key, the user biometric. So in the case of key binding, we are not going to generate the key itself from the user biometrics. Instead, the user biometrics are going to be used to bind the key and basically transform them in such a form such that going back from that to the original key is going to be very difficult. So here the key is generated randomly or using some any other method, but to secure the key, we are going to use the user biometric. So we can see the key binding process here. We have a mathematical function that is going to give us, we are going to give it cryptographic key that is generated and the biometric data as input, and it is going to give us some helper data. This helper data can be passed to this inverse function that again takes the biometric data and it gives us back the crypto key. So this helper data basically acts as the transformed version of the key, which without the user biometrics is not going to give us back the crypto key very easily. Like the only known feasible attack would be a brute force attack. So regarding the literature survey and related work, so for the minor project, I have gone through all of the current work that has been done in this field and referred to many state-of-the-art and highly cited papers in this field in both key binding and key generation. To gain a more practical understanding, however, I have implemented and thoroughly examined these two papers, which I'm going to discuss further. So let's take a look at the first paper and the approach that it uses. So it is titled A Novel Approach to Fingerprint Biometric-Based Cryptographic Key Generation and its Applications to Storage Security. So it is going to use the fingerprint biometric. That is the yeah, singular points that are present with the fingerprint to generate a cryptographic key, as I have already mentioned before. So this the key that is generated is called a biocrypto key, and the generated key is hard to crack and does not need to be remembered or stored anywhere. So as I already mentioned, storing the keys is dangerous and remembering the keys is not possible. That's why we are going to use this fingerprint to generate this key. And every time using the fingerprint biometric of the person, we can generate this key, and the scheme ensures that the same key generated each time. The parameters remain the same. So the method generates the keys in a way that it is orientation dependent and independent and highly resistant to noise in the biometric data. So what this scheme also ensures is that if we change the orientation of the fingerprint image a little bit, or maybe we capture a new fingerprint image, the singular points will remain the same, but the orientation of them is going to change. So we do not need to physically reorient or transform the singular points to a form where it has to be same as the one while generating the key. We can just use a new image, and uh, using that image, we can generate the same key using a different instance of the same biometric. The keys can be used to encrypt and decrypt messages using the standard cryptographic algorithm. As you can see, the paper claims that the key can be generated up to 1024 bits in size. So we can use AES with these. We can use some part of the key, or using these 1024 bits, we can generate many keys to generate many ciphertexts and so on. For authentication of the user, a transductive SVM ranking model has been utilized. So again, we to make sure that the genuine person is accessing, or genuine person is going to give us the basically the biometric, and to generate the key using that biometric, we're going to use an SVM ranking model instead of the usual threshold-based methods. So this is a brief overview of the key generation process. So we have a fingerprint image here. We're going to divide the fingerprint image into blocks. Now each of these blocks might contain some singular points. The singular points can be anything such as a core point, delta point, or even the minutiae that are present in the fingerprint image. We are going to compute the pairwise distance between each set of singular points. So let's say this block right here has some one singular point, let's say a core point. We are going to take this core point and compute the distances, that is the Euclidean distance, and to each point present in the other blocks. in all of these other blocks. So let's say there's a core point here. We're going to compute the distance to each and every point in the other block. And all of these are stored in such a form. So you can see the length from one block, from any singular point in the block, is stored to each of the other points is stored here, like this. And we also store the angle. So basically, there is going to be a line from, let's say, this core point here to another minutia here. We also need to store the angle that this line forms between these 2 points with respect to the x-axis. So this is an example of the fingerprint image with the singular points are highlighted. So we are going to divide this image into blocks as we have seen before, and then compute the lines and angles between all of them pairwise. We're going to do that. So taking a look at the key generation process, here we have the line lengths and angles. We're going to XOR these line lengths and angles together. So we're going to take the binary form of the line length, binary form of the angle, and we're going to XOR them together. And then we're going to concatenate them together to get a bit string. Further, what we're going to do is that we're going to pass this generated bit string, you can see this one here, through a substitution box. For my implementation, I have used the AES substitution box, but the substitution box really needs to be the same with all the parties that are going to try to generate this key to ensure that the same key is generated each time. And this substitution box can be really private, and it should ensure that it diffuses this binary string across all of the binary keys. And also, in case the key size is not large enough, we are going to use an expansion algorithm to make sure that the key is of the desired size. So here we can see that the biocrypto key is generated, right? So here we have the biocrypto key that is generated, and we can use this key to encrypt and decrypt messages. So now let's take a look at the user authentication mechanism using the transductive SVM ranking. For user authentication, we need to verify if the biometric attributes are matched with any user. So let's say we have a ciphertext that has been generated using the key generated before. Now to decrypt it, we need the user that provided the biometrics for the original key to provide their biometrics again. Now when they provide their biometrics, we are going to compute certain line attributes that I will talk about. And then these line attributes need to be verified with the help of a transductive SVM whether they belong to the person. So basically this is for authentication, whether the person is actually who they claim or not. So this SVM ranking mechanism is going to output a rank for each genuine user in the system, and the most likely user is going to have the lowest rank. So let's say there are n people in the system that are going to be there. One of them is going to provide their biometrics and claim that I am the user present in the system. And then the SVM ranking mechanism will try to figure out if they are actually not there, and if they actually are who they claim, the user is authenticated and we can use the key for decrypting the messages. This mechanism is chosen because it eliminates the need for a threshold-based authentication and instead directly compares the unique attributes for each user. So in traditional bio-crypto systems, what is used is that if 50% or let's say 70% of the biometric data matches with the stored template, then we say that this person belongs to the system or they don't belong to the system. That is the threshold-based authentication. The SVM ranking mechanism is going to output a rank for each user in our system. And so basically this system will overcome all the shortcomings of the threshold-based mechanism. Also, we are going to generate a code word which acts as the user authentication string using these line lengths and angles that we have computed before. And the line attributes that are used for this SVM ranking are just basically the length ratio. So let LK be the length of a line going from one block to the other block, and LJ is the same but for a different set of blocks. The length ratios is going to be the pairwise set of all of these length ratios, and the angle difference is also going to be the difference between the angles between a line going from one of the blocks to other block, and AL here is the different line going from a different block. This is basically what ensures that this approach is orientation independent. So here we don't really need to know the coordinates of the minutia points or the singular points with respect to any particular axis. Whatever the orientation, the length ratios and angle differences are going to remain the same. So that is why this mechanism is used with the help of a transient ranking SVM. So let's briefly take a look at this as well. So basically, the SVM ranking model is trained on a set of line attributes of the users in the system. So the length line attributes are computed for each user in the system by taking their biometric data and basically training the model on this. And then when we want to authenticate the user to, let's say, decrypt a ciphertext, what we're going to do is that we're going to retrieve the length ratio and angle differences from the code word. So they're going to provide their biometric data, and we're going to retrieve the length ratios and angle differences from that. And we need to give the input to the ranking SVM model. So ranking SVM model is going to output whatever is the rank for the user. And if, let's say, the user claims that I am some user X, and the model also says that, okay, the line attribute that I have gotten also belong to this user X. So then the user is successfully authenticated. And then we can regenerate the key for the authenticated user, and then we can decrypt the ciphertext that we have. So this is how the user authentication works, and regeneration of the key also is going to be important here. So that we can do. So this paper has been implemented for the minor project and using the FCC 2004 fingerprint database. This is the fingerprint verification competition 2004. It's a very standard database. The authentication mechanism has been implemented for the above using transitory ACM ranking model, and we have been able to achieve an accuracy of up to 86%. It is possible to regenerate the exact same keys each time using Reed-Solomon and decoding process and error correcting in the case of a corrupted code word. So whenever this code word is sent along with the ciphertext, if, let's say, some bits of the code word are corrupted during transmission, it is possible to correct those bit errors, and then we can again decrypt, decode the code word, run the whole authentication mechanism, and then regenerate the exact same key each time. This proposed approach is going to basically ensure that the keys generated have a large enough size to be used with any modern symmetric cipher. So I'll show in the further slides as well. The keys are large enough, and then we can maybe pass the large enough keys through a key derivation function and get a set of keys that are generated using these fingerprint biometrics. And they can be used with any modern symmetric cipher for, like, as a using as a private key and for both encryption and decryption of plain text. So we can see using the method, this is the key. You can see that it is completely random. It does not have any correlation with, let's say, any uh, like it would be really impossible to go from this to any user biometric. So it also is going to secure that. And using this large enough key, we can encrypt and decrypt, basically ensuring that secure communication can take place. Also, this is the Reed-Solomon code word that is generated, and this Reed-Solomon code word is basically sent along with the ciphertext uh, that will be encrypted using the key shown above, shown before, and this is basically what is going to be used for authentication. So this is the results of the authentication mechanism that are used. We are able to get approximately 86.96% accuracy using the transactive SVM model. So now let's also take a look at a key binding scheme. So this second paper is titled "A Novel Biocrypto System Based on Cryptographic Key Binding with User Biometrics." So this key binding scheme, instead of encrypting the key or maybe securing the, maybe generating a new key, it is just going to transform the key using the user biometrics, so that getting the original key back just from the helper data that I showed before is not going to be feasible without the help of the biometrics. So the biometrics here act as a key to unlock the cryptographic key. Uses the nonlinear minimization techniques to bind the cryptographic key with the biometric data of the user. So this nonlinear minimization refers to finding the minima for a given function, and those minima can be used to bound the cryptographic keys with the biometric data. The objective function is also so chosen such that there exists enough minima to bind the bio items with the cryptographic keys. So for each crypto item, which is basically a subsequence of the cryptographic key, there should be one bio item which can be bound using the minima of the objective function, and we get the cryptographic, uh, basically secure the crypto key using this. Also, this objective function is not much affected by the uh, noise in the biometric data, because biometric data tends to be very noisy. So this objective function will work as long as there is a certain amount of noise, uh, and it will not really affect the key retrieval. Key retrieval here again refers to presenting the user biometrics and getting back the original key. So this is the objective function that has been proposed in this paper, and basically we can see that we found this function, which here this chi of I can be replaced by a biometric item. A biometric item is again a subsequence of the bio key, and the bio key is just the user biometrics presented as a binary string. And here we can see that after applying all these mathematical functions, we're going to get something called a helper data. This helper data is going to help us retrieve the key. So basically, after when we want to get back the original key, we can just provide the helper data and the user biometrics to get back the original key. So this is the key binding approach that has been used. For my future work, I'm going to develop, we are working on developing a novel crypto system that uses multimodal biometrics. So until now, both the schemes that have been used are going to only use a single biometric. Let's say the first paper used fingerprints, the second paper has used iris data to basically bind these keys. But the multimodal biometrics are going to have this benefit that even if one of the biometrics, let's say the fingerprint, is captured by the adversary, it still cannot decode the key or get the ciphertext without the help of the other biometrics. So in multimodal biometrics, we're going to use a combination of biometric, let's say a fingerprint, iris, and we can use, let's say, a palm print. So all of these together are going to be required to decode the key. So it is going to help us that. Also, I'm trying to incorporate fuzzy extractors such as fuzzy vault, secret sharing, and even cryptographic commitment schemes in the crypto system to make the system robust against noise in the biometric data. This is also going to improve the accuracy of the system, as fuzzy extractors are going to allow not only allow for noise in the biometric data, but also if not all of the biometric data match with the stored biometric data, it will be possible even if a certain part there. If there's a partial overlap and if it is more than a threshold, the fuzzy extractor is going to correctly authenticate the user using the biometric data. So these are also going to improve the accuracy of the system and authenticating the user.